So let's have the Friedman's F test for randomized block design. The research designs that pair or group participants based on a common characteristics. For example, uh, common characteristics which is called randomized block design, or the designs that observe the same participants across a series of conditions, which is also known as repeated measure designs, are frequently used in an attempt to control for unwanted variability. So, the analysis of variance is a commonly used statistical method for analyzing data from a randomized block or repeated measure design. However, the assumptions of normality that underpins ANOVA is frequently violated, or the scale of the measurement for the dependent variable is ordinal level, which makes the use of ANOVA difficult or impossible in many situations. This was addressed by the person Milton Friedman, yes, who developed the statistical test based on ranks that can be applied to data from randomized block or repeated measures designs when the goal is to detect patterns in the data. So let's have this one. So the Fragments Test is a non-parametric test for analyzing randomized complete block designs, or even the randomized block design. It is an extension in the sign test where there may be more than two treatments. So the Friedman's test assumes that there are k experimental treatments, which k is greater than or equal to 2. The observations are arranged in the B blocks. So on the right, you have there the illustrations on how it was arranged rather. So in analyzing a randomized block design, sometimes the data consists of only the ranks within each block. Other times, you cannot assume that the data from each of the groups, okay, are from normally distributed populations. So in this situation, you can use the Friedman's rank test. Okay, so this would be the hypothesis. The null hypothesis for this test is the medians are the same, and the alternative hypothesis, at least one of the medians differ from the rest. So if the null hypothesis is true, the treatment effect are identical. While if the null hypothesis is false, then there is at least one treatment effect that is different from at least one other treatment effect. So note that the assignment of rank for Friedman's test does not require combining data across the group. The observation are only ranked relative to the other observations from the same block or subject. Thus, the within each block or subject, there would be rank, and unless there are ties in which we are going to use the average case. Okay, so in a summary of the table of ranks, such as the ranks 1, 2, 3, it appears in each row or the block. So we have to bear in mind that if the null hypothesis is true and all treatments have identical effect, then the ranks that appear in any treatment column of the rank summary table occurs merely by chance. Thus, when we have a true null hypothesis, neither the smallest ranks nor the largest ranks should tend to appear in a particular treatment column. So, in other words, the ranks in each block should be randomly distributed over the column or in each treatment within each block or subject. So, however, if the null hypothesis is false, then we expect a lack of randomness in the distribution of ranks in each block. So, for example, if one treatment is better than the other, then we expect to see a large ranks in that treatment column. If better implies a larger response, or expect to see a smaller ranks in that treatment column if better implies a smaller response. Um, a useful test would therefore be one that is sensitive to detecting departures from the pattern expected when the null hypothesis is true. So the Friedman's test is such a test because it detects departure in the pattern of ranks, assuming that the null hypothesis is true. The significant departures would then lead to rejection of the null hypothesis. So the Friedman's test statistic is based on the magnitude of the sums of the ranks associated with each treatment or the sum of the column ranks. If the null hypothesis is true, then we expect that the column sums to be relatively close to each other, such that any differences can be attributed to chance. If the null hypothesis is false, then we expect that at least one column to be sufficiently different in size with at least one other column such that the difference is likely to have occurred by chance alone. In this case, we are going to reject the null hypothesis. Okay, so let's have an example. So, researchers compared three methods of determining serum amylase values in the patient with pancreatitis. The results are given in the following table, okay, as shown in the right. Do this data indicate that the difference among the indicate a difference among the three methods? So in this case, we are going to first state our null hypothesis. So our null hypothesis would be we could have, since we have uh, three methods, so the median of the first method would be the same as the median of the second method. And of course, this would be the same as the third method. So it means that there would be no difference. There would be no difference on the medians, or the results of the medians of the three methods. Okay, and our alternative hypothesis would be at least uh, one of the medians is different from one another, from the other. Okay. So that is how we are going to have our, or to state our null and alternative hypothesis. Okay, let's move to our Excel. So we have here the methods, three methods, and then you have the level of the protein or the amylase. So that would be the enzyme. Okay, so we go to add-ins, megastat, and then we go to non-parametric test, and then we go to Fragments test. So in this case, we're just going to highlight those numbers. Okay, do not include to highlight the text. And then as you can see here, we can check the correct for ties, because as we can see here, I guess there would be ties here. And then if you want to get an output on the rank data, you can check this one. Okay, it's either you want to check that one or it's not. It doesn't change the results. They're just the same. Okay. Click OK. Okay, and here, as you can see here, we have tie ranks. Okay, so here, as we can see here, that the chi-square corrected for ties is 15.943. And of course, the degrees of freedom is 2. It's because we have three groups here. So the p-value is highlighted with yellow. It means that this is significant at 0.05 level of significance. So since this is highlighted, it implies that we are going to reject the null hypothesis. So as we can see here, since the p-value is less than 0.05, then we are going to it fails to reject our alternative hypothesis. Okay. So if we are going to look for which among the hypothesis rather is the claim of the researcher, we could see here that the claim of the researcher is the alternative hypothesis. So since the claim of the researcher is the alternative hypothesis, and we reject the null hypothesis, then the alternative hypothesis is true. So we could see here that at least one of the median in this tree method is different from the other. So there is now a significant difference among the methods. So again here, we could not really identify which among the three is significantly differ from one another. What the result implies here is that there is one or two, there is one uh, group here that is significantly different from one another. Okay, so that's how we are going to have the interpretation of this data. Okay, so again, in some other statistical tools, we can go for post hoc analysis to determine which among the three, okay, significantly differ from one another. Okay, the results in this test only implies that there is a group. Okay, there is a group within the three groups being analyzed that is there could be at least one group, okay, within these three groups in within the analysis that is significantly differ from one another. So that's how we are going to interpret.